All right. Hello, good morning, everybody. Welcome to everyone in Marcus and everyone joining the live stream. I hope you guys are having a good week. I apologize again about the Moodle issues. I'm not really sure what was going on there. But in case you didn't get my emails, there were some access issues to Moodle. And so the Chapter 3 quiz was extended through today. So if you were not able to submit it yesterday, it is still available today for you to submit. So as far as I know, there's not any major Moodle issues today. So hopefully those are resolved and won't reoccur. So we are starting chapter 4. And so to give you sort of big picture chapter 4, we spent chapter 3 finding how to take different derivatives formulaically, how to determine derivatives of all types of functions. And so chapter 4 says, now that we can find those derivatives, what kind of information does that tell us, right? So we know that the derivative will give us the slope of the tangent line, but we can use it for so much more. So there's going to be lots of things that we're able to learn and understand now that we have a good sense of how to take derivatives. So the first section that we're going to cover is called local maximums and minimums. It's a fairly long section, so we're going to be covering it today and Thursday. And what that means is that we don't have a mini quiz on Wednesday, and that the mini quiz for this section is on Sunday, because it's going to take us 2 days to cover it. So we're going to do the first half of it today. We'll pick up and do the second half of it on Thursday. So let's go ahead and get started. I'm going to switch over to the dot cam to get us a little settled here. And so this is sort of a goofy setup here in that we're going to be talking about something called local maximums and local minimums. So we're going to talk about what those are and what that means, but then we have to sort of take a step back to do some background work before we can even really start mathematically finding local maximums and local minimums. So we're going to understand what we're eventually trying to find. But then within the process, we have to do some other work first, if that makes sense. So what is a local maximum and a local minimum? So the definition says that a function is said to have a local maximum at some point p if f of p is greater than or equal to values of f of x near p. And a local minimum, we say a function is said to have a local minimum at p if f of p is less than or equal to values of f of x near p. So what does that mean, right? So the main part of these definitions that are really important is this idea of like near p. So when we look for local maximums and minimums, we are looking for high and low points in small areas. Okay, so what does that mean? So we're going to start by looking at this picture so we can sort of understand what we mean when we say near P. So for local maximums, right, we're looking for a high point in a small area. So here we are going to have a local maximum at this point right here. And what I want to point out is that it is not the highest point on the graph, right? There are points over here that are higher, but the local maximum is the highest point in this small area. When we talk about the highest point or the lowest point on a graph, and we're not talking about a small area, that has a different name that we call global or absolute maximums and minimums. And we're going to learn how to find those next week. So those are slightly different. So when we talk about local minimums, we're looking for the lowest point in a small area. So we can see that that actually happens here and here. So local minimums are the lowest points in a small area, right? And what you're going to notice is that our local maximums happen at the top of hills, right? Like if you imagine the graph had a hill, right? We're right at the top. That's a local max. And our local mins are sort of at the bottom of a cup. So if you imagine that the shape of a graph is like a cup that would hold water, right at the bottom is where we have our local min, because it's the lowest point in the small area. Okay, so some special notes about local maxes and mins is that functions can have more than one. local max or local min? Okay, we see in this example down here, we have 2 local minimums. That's fine, right? If they're local, it just means in their given area, right? And then, as I mentioned, local maxes and mins do not have to be the highest or lowest point entirely on the graph. So we say the absolute highest or lowest point. Now, just to be clear, they can be, right? I want you to look at this local minimum right here. So this local minimum is the lowest point on the graph, but it's a local minimum because in this area, it's the lowest point because this is also a local minimum, okay? So what I want you to notice is that as I'm drawing in and labeling these local maximums and minimums, and we find these points where we're the highest point on a hill or the lowest point on what I'm calling a cup, the thing that they have in common is that when you draw in the tangent line at that point, it's where we have a horizontal tangent line. And I want to remind you that the slope of a horizontal tangent line is equal to 0. So that's where we're going to start our work in figuring out how we find and determine local maximums and minimums. We're going to start with locating where they are. So the first step is, where do these horizontal tangent lines happen? Once we're comfortable with that, then we say, okay, well, how do we determine if the function has a local max or a local min? We know that there's something here, but which is it? But we're not ready to get to that quite yet. So when we identify places where we have these horizontal tangent lines, which again are going to happen at the bottom of cups or the top of hills, we have a special name for these places. Okay, so we call these critical points. So a critical point, P, for a function f of x is a point in the domain of the function where the first derivative at that point equals 0. So that's what we're seeing here. This is where the first derivative equals 0, or where the first derivative is undefined. So remember, we have things that are undefined if they are not continuous at that point. For us, this is mainly going to come up when we use the quotient rule, because we know that the denominator will be undefined if it equals 0. So that's the case we have to sort of file away and say, okay, if we are doing the quotient rule, we also have to check this case, the undefined case, okay? The critical value is the y value at the critical point, right? So if we know that there's a critical point at x equals 1, then the y value when x equals 1 is the critical value, that corresponding paired y value. 95% of the time, we're just looking for the x value for our critical point. So that's where we begin a lot of our work for today. We're going to be finding a lot of critical points, and we're going to get really comfortable determining where these horizontal tangent lines are. And once we get really good at that, then we can say, hey, how do we know if it's a local max or a local min? Okay, but before we can do that, we have to get really comfortable with critical points. So we are going to be over here practicing all sorts of things with algebra and derivatives today. So we're going to start with these 2 examples. So the first one, f of x equals 3x squared plus 6x plus 1. We want to find all the critical points of this function. So again, we're asking, where is the first derivative equal to 0, or where is it undefined? Since this is not a quotient rule, I'm not concerned about undefined. Same thing for example 2. We want to find the first derivative, and we want to know when does that equal 0. So for example 1, the algebra on solving for when the first derivative equals 0 is fairly straightforward. We can just do simple things to it. However, for example 2, when you want to set the first derivative equal to 0, you do have to either use the quadratic equation or do some factoring to find the roots. So it's a little stepped up from example 1. Okay, so I'm going to give you 3 minutes. I want you to try these out. And again, the process is going to be to find the first derivative using our regular derivative techniques, and then set the derivative equal to 0 to then solve that algebraically. That's how we're going to find our critical points. So take about 3 minutes, try it out, and then we will go through it together. Okay, take about 30 more seconds. Okay, so let's walk through the algebra of these. And so, as I mentioned, the first one's a little bit simpler than the second in terms of the algebra. So let's see why that is. So for our example one, we're going to be using our power rule to solve the derivatives of these. So here, the first term, the 2 is going to come down to multiply the 3, and we get 6x to the 1 power. The derivative of 6x is just 6, and the derivative of 1 is 0. So we want to know, when does the first derivative equal 0? Okay, so here we can subtract 6 on both sides. So we have a 0 pair. So we have 6x equals -6. We divide both sides by 6. We get x equals -1. So we have one critical point, and that point is x equals -1. Okay. Now for the second one, we start off again by finding the first derivative. And again, we're using our power rule here. So the 3 comes down to multiply the 2. So we get 6x squared minus 6x. Then we get minus 36 from this term here. And then the derivative of 14 is 0 because 14 is by itself. So now when we set it equal to 0, we have this x squared term and we have a constant. So we do need to either use the quadratic equation or a factor. They're going to give you the same answer either way. So if you're more comfortable with one than the other, that's totally fine. I'm going to factor this just because I like factoring. But again, if you use a quadratic equation, that's totally fine too. So when I factor, I like to pull out the number that's in front of the squared term first. It helps me sort of better visualize how the factoring will work. So I'm going to factor out a 6. So I have x squared minus x minus 6. And now I'm going to factor the x squared minus x minus 6. So I'm looking for two things that multiply to give me -6, but add up to give me -1. So I have x minus 3, x plus 2. Okay, so once you've factored something, we now have 3 factors. Okay, I have the 6, I have the x minus 3, and I have the x plus 2. I need to set each factor equal to 0 to find my solutions. If I set 6 equal to 0, there's no solution, so that doesn't give me anything. If I set x minus 3 equal to 0, I get x equals 3 as a solution, because that would make this first term 0 if x was 3. And then I set x plus 2 equal to 0. So I get x equals -2. So this function has 2 critical points at x equals 3 and x equals -2. Okay, so again, I'm utilizing this idea that I'm interested when the first derivative is 0 or undefined. I didn't have anything undefined because, again, I don't have any denominators here. Okay, so these I would say are sort of your standard types that you will see for finding critical points, where you'll have an algebraic function that is polynomial terms. However, we can obviously have more difficult derivatives and still do this process. So the next 2 examples that we're going to look at are going to be more difficult in terms of the derivative technique, which in turn can sometimes make the algebra a little more difficult. That doesn't mean you can't do it. It just means we need to be more careful with our steps as we write things out. So for examples 3 and 4, we're going to try some that are a little bit more, that we have to be a little bit more careful. So for example 3, we're doing, I'm going to write this a little bit bigger, x squared over x minus 2. So here we're going to have to use a quotient rule. And when we do the quotient rule, we do have to also consider where the first derivative is undefined. Okay, so we're considering what's happening with the denominator. For example 4, we have x cubed times 1 minus x to the 4th. For this one, we're going to be using a product rule first, because we have the x cubed and the 1 minus x to the 4th. But within the product rule, we have to use a chain rule when you're finding the derivative of 1 minus x to the 4th. Okay, so again, these derivatives require a little bit more attention than just our polynomial terms. So we do have to be fairly careful as we're doing out all our steps. So I'm going to give you 4.5 minutes to try out these 2. You can pick whichever one you want to do first. You don't have to do them in this order if you're more comfortable with one than the other. But as a reminder, you know, your first step is to find the derivative, which is what we've been practicing in chapter 3. But then we need to set it equal to 0. And that's where some of the algebra comes back in when we think about factoring or what it means to equal 0. So if you don't remember those things right now, that's okay. Just do your best to get the first derivative, and we'll go through them together, like I said, in about 4.5 minutes. Okay, so try those out, and then we'll go through them soon. Okay, take about 30 more seconds. Okay, so let's start with this quotient rule. So we have x squared over x minus 2. When we set up our quotient rule, our top function is always our f. So that's the x squared term. And our bottom function is always the g, the x minus 2. We need to take the derivative of each of those respective functions. So the derivative of x squared is 2x, and the derivative of x minus 2 is 1. So now we need to plug this into the quotient rule. So we're going to do f prime times g. So we have 2x, and I'm going to use parentheses because there's two terms for g. So that's x minus 2 minus g prime times f. So 1 times x squared, all divided by x minus 2 squared. Okay. So again, if we were just trying to find the derivative, we wouldn't need to do any simplification, but now we are going to ask the question, when does this equal 0 and when is it undefined? And so in order to answer that, we do need to simplify this. So I'm going to start by distributing the 2x through this parentheses. So I get 2x squared minus 4x, and then I still have minus x squared, all divided by x minus 2 squared. So notice that I have a 2x squared and a minus x squared. So I'm going to combine those, and that's going to give me x squared minus 4x divided by x minus 2 squared. So that's the first part of this, is being really careful about setting up these derivatives, getting this set up, and then distributing properly. So make sure if you were missing any of those steps that you're taking careful notes. And so then here we finally have a simplified version of our derivative. And now we need to answer the question, when does this equal 0 and when is this undefined? So if you have a quotient function like this, okay, and you want to know when it equals 0, we need to set the numerator equal to 0. That's when the whole function will equal 0. So I take the numerator, x squared minus 4x, and I set that equal to 0. Looking at the function I have, I notice that I can factor out an x. So I have x times x minus 4 equals 0. So I have two factors, right? I have x and I have x minus 4. So I set them each equal to 0. So x equals 0 gives me x equals 0. So I'm going to keep my critical point list over here. So x equals 0. And then x minus 4 equals 0. If I solve that, I get x equals 4. So I get two critical points by setting the numerator equal to 0. To determine if this function is undefined, I need to take the denominator and set that equal to 0. So I have x minus 2 squared equals 0. So here, if x equals 2, that will make this whole thing 0, which makes the squared version also 0. So I also have x equals 2 as one of my critical points, because that is where I am undefined. So I have three critical points from this function: x equals 0, x equals 4, and x equals 2. Okay. One thing I want to give you a heads up about is oftentimes on Wiley, it's going to ask you to enter these in increasing or decreasing order. So if it asks you to enter them in increasing order, you'd put in 0 and then 2 and then 4, right? Getting bigger. You can't just put them in whatever order you want. If it asks you for a specific order, make sure you put them in that order. Okay. Now, for example 4, there's some more algebra and stuff that we're going to need to do. So let's take a look at this. Again, we have a product rule because we have an x cubed times 1 minus x to the fourth. So we start by separating those. Our f is going to be x cubed and our g is going to be 1 minus x raised to the fourth power. Then we need to find each of their respective derivatives. The derivative of x cubed is 3x squared, just using the power rule. But the derivative of 1 minus x to the fourth requires a chain rule. So I did this all in one step, but you certainly can do it in multiple steps. I'm going to do the work just a little bit on the side so you can see where I came up with that. I'll do it right above. So I was using the outside inside rule for parentheses to a power. So I started by doing the outside part of it, and the 4 came down, everything inside stayed the same, and I subtract 1 from the power. But then I have to multiply that by the derivative of the inside. The derivative of 1 is 0 because it's by itself, and the derivative of minus x is negative 1. Okay, so don't lose that negative. That's really easy to miss. And so what I did is I simplified this just by bringing this negative 1 to the front. So negative 4 times 1 minus x cubed. Okay, so that's the first part where we have to be really careful. Now, we need to put this all together within the product rule. So the product rule says we're going to do f prime times g. So we have 3x squared times 1 minus x to the fourth plus g prime times f. So negative 4 times 1 minus x cubed times f, which is x cubed. Okay. So once we have all the pieces there, again, if we were just looking for the derivative, we wouldn't have to worry about factoring or simplifying or anything like that. However, we want to answer the question, when does this equal 0? And so in order to answer this, we do need to factor it. And so when we factor something that looks like this, we have to really consider what the common terms are between these two different parts of the function. Okay, so first I noticed that both parts of the function have x terms, right? This one has an x squared, this one has an x cubed. I also noticed that both parts of the function have this factor of a 1 minus x raised to a power. And then I also consider the constants. So I noticed that the constants are 3 and negative 4. Those two numbers do not have a common factor. So I'm not going to pull out any sort of constant, okay? So when thinking about what to pull out, let's start with the x term. I have an x squared and an x cubed. When you factor, you want to pull out the lowest power in your terms here. So the lower power is 2. So that means I'm going to be pulling out an x squared. And then when I consider the 1 minus x terms, I'm going to think about the same thing. So for the 1 minus x terms, I want to take the one to the lowest power. So this one has a power of 4. This one has a power of 3. So I have 1 minus x cubed. I take the lower power. And now that I've pulled those out, I have to see what's left. So from the first term, I still have my 3 because I didn't pull out any constants. I took out the entire x squared, and I took out 3 from the 4 1 minus x terms. Since I took out 3 of them, that means that there's 1 left, 1 minus x to the 1 power. Now from the second term, I still have my constant, minus 4. The 1 minus x term is to the 3. I pulled out 3 of them, so I pulled out all of those. And then from the x term, I had x cubed, but I pulled out 2 of them, which means I'm left with an x to the 1. So that's what the inside parenthesis looks like once I've pulled out these two terms. Now, what I notice is that I can actually simplify this parenthesis, this last parenthesis here, by distributing the 3 to the 1 and to the minus x, and then combining the terms that have an x. So I'm going to go ahead and do that before I completely jump to my solving. So again, I'm just simplifying what's in the bracket terms here. If I multiply this through, I get 3 minus 3x. And then the minus 3x and the minus 4x combine to give me minus 7x. Okay. And I want to know still, when does that equal 0? Because this is still my first derivative. I just factored it fully with all the terms. And so now I have 3 different factors. 1, 2, 3. I set each one equal to 0 to find the places that's going to make this whole thing equal to 0. So when I set the first one equal to 0, that's x squared. If I have x squared equals 0, the solution to that is x equals 0. That's my first critical point here. When I take the second parentheses and set that equal to 0, I have 1 minus x cubed equals 0. So I'm really looking at what makes the parenthesis equal to 0, which is x equals 1, is my second critical point. And then my third factor, I'm taking 3 minus 7x equals 0. So I do have to do a little rearranging here. I can bring the 7x over. I'm going to divide both sides by 7, and I get my third factor, which is x equals 3/7 when I solve this last one. Okay, so I had to do all this work of factoring so that I could then set each one equal to 0 to find my 3 critical points. Okay, so this is not trivial, right? There's a lot of steps here, and we have to be really, really careful and try to stay as organized as possible within the work. So I'm going to encourage you, when you do some of these harder or longer types of problems, to write out your steps carefully so that if you mess something up, you can easily go back and check your work and try to figure out where you went wrong. Okay, hopefully that doesn't happen, but just in case, the more organized you are, the easier it is to sort of identify what may have happened. Okay, so we are going to go a little out of order. I'm going to skip to 7, 8, which are still algebraic, and then we'll come back to 5, 6. Okay, so staying on this idea of solving algebraically for critical points, we sometimes have functions where when we are trying to solve, we have something that's more generalized than the specific types of functions we were just looking at. So something like ax squared plus bx minus c, where a, b, and c are non-zero constants, right? So we're still trying to apply the process, but now we have added in this layer where we have variables representing constants. So for example, 8, you see we have ax times e to the negative bx. So again, a and b are going to be non-zero constants. So we want to make sure that we can still solve for these things even when we don't have the specific numbers, but more of a general form for these equations. So that's sort of what we're looking at here. So we want to find the critical points of these two functions. So again, we're going to take the first derivative, we're going to set it equal to 0, and we're solving for x. X is the variable in both examples 7 and 8. For example 7, when you take the derivative, you can solve just algebraically by moving some things around. But for example 8, you do need to do a little factoring in order to get to the final answer. So I want you to try these out. I'm going to give you 3.5 minutes-ish to try them out. Try your best, see what you can do. And just as a reminder, again, A, B, and C in the first part and A and B in the second part are constants. They're non-zero constants. We just don't happen to know what they are. So they could be 1, 5, 12, right? We're just doing it sort of more generalized. So try that out, and then we will go through it together. Okay, take about 30 more seconds. Okay. So we have to be a little more careful when we think about these because we do have this extra added generalized factor of constants here. So again, we see the word critical points. We're thinking, okay, when does the first derivative equal 0? Okay, so let's see. Let's do this up here. So for the first one, when we take the first derivative, we have ax squared. So the a is a constant multiple. The 2 is going to come down, and we get 2ax plus, now the derivative of bx is b, and the derivative of minus c is 0 because the minus c is not attached to an x. So when we're talking about critical points, we want to know when does the first derivative equal 0? And what's really important here is that we remember what the variable is. The variable here is x. So that's what we're trying to solve for, right? So we can subtract the b over to the other side. We have 2ax equals negative b. We divide both sides by 2a. We get a 1 on the left, 2a over 2a is 1. And so we get x equals negative b over 2a. So we are able to successfully solve for this critical point, even though we don't have the values for a, b, and c. We're able to solve for it in a more generalized way. So this is how we represent the critical point. Okay, so again, x equals negative b over 2a. Now, when we think about this for example 8, again, we have to be a little bit more careful here because we do have a product rule to start with, and then the algebra of the factoring is a little bit more tricky. So let's see how this all shakes out. So because we have a product rule, I have ax and e to the negative bx. So I'm going to call my f ax and my g e to the negative bx. So when I take the derivative of each of these pieces, the derivative of ax, a is a constant, so the derivative is just a. And when I take the derivative of e to the negative bx, the negative b is a constant, so that comes out to multiply e to the negative bx. So remember, when there's a constant in the power, that constant comes out. So when we put these together now using the product rule, we have f prime times g, so a e to the negative bx plus g prime f, so negative b e to the negative bx times ax. So my derivative looks like this, and I know that I'm going to want to set my derivative equal to 0. I would like to do a little rearranging before I factor. You do not have to do that. This is just a matter of preference. So I'm going to keep the first term exactly the same. But for the second term, I notice that I have plus and then a negative. So I'm going to turn that into a minus. I like to pull my constants to the front. So I'm going to pull that a up to the front to be with the b. I'm also going to pull my x to the front, and then e to the negative bx. So this is a matter of preference for me. Commonly in math, we write things in decreasing order of difficulty or increasing order of difficulty in a term. So constants and then x terms and then e terms. But you could leave it like this and still be totally fine. Okay, so we want to know, when does that equal 0? Well, in order to determine when this equals 0, we do need to factor it. And so what I'm looking at again is what do these things have in common? I notice that they both have an A. So I'm going to pull that out. And I notice that they both have the E term, e to the negative bx. So if I pull that out, the question becomes, what am I left with? So from the first term, I took everything, right? If you take everything when you factor, you put a 1 placeholder there. So again, if you were to multiply that back in, you would just get the whole thing. Minus, now here I took out the A and I took out the E term, which means I'm left with a BX. So I'm left with something that looks like this. And again, I have 2 factors, this one and this one. And I want to know, when do they equal 0? Well, you may or may not remember this from algebra, but the E function, e to the negative bx, is never going to equal 0, right? It doesn't cross through the x-axis. There's no value of x that you can plug in that will make that equal to 0. So the first factor will never equal 0 because a and b were just non-zero constants. So that means I can just focus on the second factor. The second factor, I have 1 minus bx equals 0. Again, I'm trying to solve for x. So I can have 1 equals bx by bringing this term over, and then I divide, and I get x equals 1 over b. So that means that the critical point for this generalized function is 1 over b. So if I knew the value of b, if I knew b was 7, right, then I would know that the critical point is 1/7. If I knew b was 10, I would know the critical point is 1/10, right? So I'm able to find a general way to talk about this critical point, okay? So that's on sort of generalized critical points. The other way that this is going to come up for us has to do with the fact that we're using this definition of critical points. And within the definition, we can extend this to things that are not algebraic, okay? So we can also do this on, say, a graph or a table, which we'll do after the graph. Just stick this underneath. So as a reminder, the critical point is going to happen when the first derivative is 0 or undefined, okay? So if I have a graph here, and I'm told that this graph is f prime of x, and it's given below, we want to use this derivative graph to determine the critical points of the original function, okay, on this interval -2 to 8, which is the entire interval. So I want you to think about this definition we have for critical points. I want you to think about how we can apply that to this derivative graph to help us understand what the critical points of the original function are going to be. Okay, so take a minute to think about it. Label any points that you think are critical points of the original function on this derivative graph, and then we'll go through it together. But I want you to take a minute to really think about it, to guess where the critical points are going to be of the original function, and go ahead and write them down somewhere. And then we'll go through it in about 1 minute. Okay. So our definition says that the critical points of f of x, so the critical points of an original function, which is where the first derivative is going to equal 0, or when the first derivative is undefined. Now, what we have here is a picture of the first derivative. So let's talk about undefined first. If the function is undefined, that would mean it has something that's not continuous within this function, right? We talked about continuity back in chapter 2. There's no holes or asymptotes here. So there's no places where the first derivative is undefined in this graph. So we don't need to worry about condition 2. So we go back to condition 1, when the derivative equals 0. So we have to remember now what that means on a graph for the function to equal 0, because this is a graph of the derivative function. The derivative function is going to equal 0 whenever we pass through the x-axis. So that happens 3 times, right? The first one is at x equals 0, and then again, roughly 3.1, right? This is going to be pi, but you can approximate it to 3.1. And then again at 6.2. But the idea here is that we recognize that in order for the first derivative to equal 0, we are considering where we cross through the x-axis. That's where f prime equals 0, okay? And that's where we have critical points for the original function. So that's how we would analyze that type of graph to give us information about the original function, okay? The next example is similar, but now we have a table. And so we're going to ask the question, how do we use the information from the table, which gives us information about the derivative, to talk about the original function? So in this scenario, f of x and f prime of x are continuous functions that are differentiable. They're both continuous, so we don't have an undefined situation. Given the table of the derivative values, determine the most likely places that f of x would have critical points. Okay, so I'd like you to take another minute, look at this table, think about what we know about critical points, think about what we know about continuous functions, and see if you can figure out where we might have any critical points, okay? Okay, so again, when we talk about critical points, since both functions are continuous, we don't have a case where they're undefined. So we're really interested in when the first derivative might equal 0. So if we look through the y values, we see that at x equals 6, we have a place where the first derivative equals 0. So this one is the easier of the two because there's another one sort of hidden in this table. So if we know that the derivative equals 0 at a point, we know that that's a critical point, okay? Now, thinking about continuity, in order for a function to change signs, so to go from positive to negative or negative to positive, it has to go through 0. We see that happening here, right? So we went from -4 to +5, and in between, we crossed through 0. But that happens again over here, okay? So we go from +2 to -1. In order for the derivative to go from +2 to -1, it has to cross through 0 if it's continuous. So that means we also have another critical point between x equals 10 and x equals 12. So somewhere between these two values, we have to cross through 0 again. So there's sort of this hidden critical point as well on this table. Okay, so that's a little tricky. Okay, so now that we've talked about critical points and how to find them algebraically, which is what we do most of the time, but also graphically with information about the derivative and on a table with information about the derivative, the next step is saying, okay, once we have these critical points, how do we determine if they're local maxes or local mins, right? That was sort of where we started this journey. So here's what we're going to do, okay? There's the short answer to this is that it depends, okay? And so what we do is we call this classifying critical points. So the first step in classifying critical points for all the ways we do this is to find the critical points, right? That's what we've been working on the first half of class. So once we have the critical points, determining whether they're local maxes or mins depends on the type of information you have. Okay, so the first way that we're going to classify critical points is using information about the original function. So that means we mainly have information about f of x, and we want to use that to classify what's happening with our critical points. So we're going to start with this example here. So we have the function 4x cubed minus 6x squared minus 72x plus 12. So what I would like you to do is I would like you to, step one, find the critical points. That's what we've been doing all class. So we want to find the first derivative and set it equal to 0. And then once we have the critical points, what we're going to do is we're going to look at a graph of the original function and use that to help us understand whether our critical points are local maximums or local minimums. So if you have the notes printed out, the graph is on the next page. If you don't have the notes printed out, we'll look at the graph together. But I want you to take 2 minutes and find the critical points of this function, and then we'll take the time to learn how to classify them. Okay, so take 2 minutes, and then we will go through it together. Okay, take about 30 more seconds. Okay, so whenever we are trying to identify local maximums and local minimums, the first step is always to find the critical points. So we are always looking at the first derivative and when it equals 0. So here, the first derivative we can find algebraically. So when we take the derivative here, we're going to get 12x squared minus 12x minus 72. And we want to know, when does that equal 0? So again, you can use the quadratic formula, you can factor, you may factor differently than I factor. All of that is fine as long as you're coming to the same conclusions. So I'm going to pull out a 12. I'm left with x squared minus x minus 6. So again, with a negative 6, I'm going to have x minus 3, x plus 2. I check each of these, set them equal to 0, and I get 2 critical points. I get x equals 3 and x equals negative 2. Okay, so that's always step one, is just finding your critical points, because you can't classify them until you find them. So we have our critical points. Then how do we use the original function? Well, typically you're going to be using the original function because you have a graph of it. And so this is what the graph of our function that we just looked at looks like. So this was 4x cubed minus 6x squared minus 72x plus 12, right? Our critical points were x equals 3 and x equals -2, okay? So we have our critical points, and what we're saying now is, how do we determine what they are based on what this graph looks like? Well, for x equals 3, we go over to roughly where 3 is. We go down till we find that horizontal tangent line, and then we visually look at what's happening on the graph, right? We see that this is the bottom of a cup, and that tells me that that is a local minimum. Similarly, at x equals -2, that means we're going to the left, so -2 is roughly here. We find our horizontal tangent line. We look at what this visually looks like, and I see that this is a local maximum. So we are able to visually inspect the graph to determine what type of critical point it is. Now, formalizing this into rules, this is what we're doing when we visually inspect, okay? So suppose that P is a critical point of your function. If your function goes from increasing to decreasing around P, so it's going up and then it's coming down, then you have a local maximum, right? If you go up and then down, that makes a hill. If f of x changes from decreasing to increasing, so going down and then up, that's going to make a cup. That's going to give you a local minimum. And if it does not change around P, then it's neither. So let's talk about this neither case real quick. So you could have a graph that looks, I don't know, like, let's say, like this, okay? So on this picture, we have a local minimum here. That's a critical point. We have a local maximum over here. That's a critical point. But we also have a critical point that will be identified here. And this point is neither, because it's not the bottom of a cup or the top of a hill. It's like a weird flat spot. So if your graph sort of flattens out but doesn't create this like hill or cup, that's when you have neither. Okay, so what we want to do is we want to start thinking about what the graphs of all of these functions look like that we've been working with so far. So what you're going to notice is that we are going to go back through all of the examples that we have already found critical points for, and now we're going to start classifying them. So for example, example 1, if you look at your notes, was the example 1 that we did, before. So we already have the critical points, right? But now we're going to try to classify them. So we're going to do example 1 and example 2. So again, these are the first 2 ones that we did on the critical points before. So we actually already know the critical points. It's good to double check them. But what I would like you to do is make sure you know the critical points. So you can either redo it by finding the first derivative, setting it equal to 0 and double checking it, or you can copy it from earlier. But then you want to graph the functions, the respective functions, look for where that critical point is and determine, is it a local max? Is it a local min? Is it neither for each of the critical points? So this one had 1 critical point. This one had 2 critical points. I want you to try that out because I want you to be comfortable with graphing them. So then we will sort of go through it together. So what I'm going to do is I'm just going to write down what the critical point was. If you want to double check the math on it to just practice, that's fine. So this is x equals -1 for this critical point. We had 2, so we had x equals -2 and x equals 3. And we are trying to figure out were these local maximums, local minimums, or neither by graphing the original function and looking at what's happening at that point. Okay, so take 2 minutes, try to graph those out. If you don't have a graphing calculator, you can certainly pick some points and try to give a general plot, or you might know what the shape is based on how familiar you are with algebra, but take 2 minutes and see what you can do in terms of classification, and then we will go through it together. Okay, take about 30 more seconds. Okay, so again, for example, 1, if you double check the derivative, we have 6x plus 6. You set that equal to 0. That's how you get the x equals -1. If you are to graph the original function, you get a parabola that looks roughly like this. And you can see pretty quickly that if we come over here to roughly where -1 is going to be, right, you're going to come down. The horizontal tangent line is here. This is at the bottom of a cup. So that makes your critical point a local minimum. Okay, so we're visually inspecting the original function to determine the type of critical points. The second one I did on my calculator, so I can show you the syntax in case you have a similar type of calculator. I have a TI-84. This is sort of the syntax for most of the TIs. I went to my y equals and I plugged in the original function. So 2x cubed minus 3x squared minus 36x plus 14. I did have to fidget with the zoom a little bit. So I went to the window. Since my critical points are -2 and +3, I made my x values -10 to 10 because that will capture both of them. And then I had to make my y values kind of big in order to see it because otherwise my graph was going way off. And then I hit graph and I get something that looks like this. And so again, I know that my -2 critical point is the one to the left of the y-axis, right? The negative values. And so I see that this is going to be a local maximum. And then for +3, I know that that's the one to the right of the y-axis, right? I just kind of visually look here and I see that that's a local minimum. There's not a lot of conflicting information on this graph, so I'm more easily able to tell. But if I couldn't tell which one was which, if I had maybe I don't know, 1 at 0 and 1 and 2 and 3, and I had a lot. You can certainly use the trace function to go over, and you can sort of see the x values over here. So you can go over until you get to roughly x equals 3, and then you would know that that is, you know, where this particular one is, if there's a lot that you're trying to distinguish between. But we're just looking at the graph to determine whether these points are local maxes, local mins, or neither. So what we're going to be doing, we're going to continue doing this for the other problems that we've already solved for the critical points here. But we're going to stop here for today. If you want to try these out on your calculator before Thursday, that's fine. But that's where we'll start on Thursday. We'll graph these and check the critical points that we already found, so we get comfortable classifying there. And then we'll move on to the other tests that we'll be doing as well. Okay, so on the homework, definitely try the problems that are just about critical points sooner rather than later. And then you can do the other ones after class on Thursday in the classification. Okay, so have a great rest of your week, and I will see you all on Thursday.